All right, we're going to proceed to do problem number 2 of homework number 4. Basically, problem number 2 gives us several functions. Specifically, it gives us a y equals g of x, gives us little f of x, which is basically the probability density function in terms of x, which we can get the big F of x, so the cumulative function from that. Given this, what the question asks us to do is to calculate little f of y and big F of y, as well as to draw them out. So before we proceed, it's actually worthwhile to look at what's given to us. Specifically, because we're going to be referring back to it several times, we're going to be looking at this g function right here. And we have the corresponding picture drawn out right there. As we can see, basically how we define is that for x is less than 0, so right here, we have y equal to 1. All right. From 0 to 1 on the x-axis, we have y equal to 0. So we basically have a jump right there from this line down to this line. Then from 1 to 2 on the x-axis, we correspond to this linear term, a negative x term. All right, so it's a negative linear term right here, from 1 to 2 on the x-axis. All right, and then on the x-axis for values greater than 2, we have y equal to negative 2, so this straight line right here. Okay. Now this is going to be important when we start looking at our functions in terms of y, because we're going to be looking at this term right here. Basically, we're going to be looking at this graph kind of in reverse. I might be jumping the gun a little bit, but we're basically looking from the range. The y range from negative 2 to 1, but we'll get there in a minute. Just quickly mention, it's not given us explicitly, but the little f of x is drawn out like this within the problem, and we can see it's basically a normal distribution, and we can create a rough sketch of the corresponding big F of x, which is just a sinusoidal curve. So that's what's given to us, and we're asked to figure these two out. So let's dig in. Now we're going to start by looking at the little f of y and deriving that equation right there, okay, which we'll go through in a minute. Now, just to go back for a second, as I mentioned, we're going to be working in a range on the y-axis between negative 2 and 1. All right? So if we actually flip, take a look at this figure like so, we can actually see certain parts of the y-axis we're going to be more interested in. We're going to be interested in the y-axis where y is equal to negative 2. Our biggest issue is going to be this range of y between negative 2 and negative 1. We have this negative linear term. We're going to have a jump here, which isn't defined on the y-axis between negative 1 and 0, so that's not going to be a big deal. But then we're going to have values defined at y equals 0. Right here, we have a jump on the x-axis from 1 to 0. This is also not defined on the y-axis between 0 and 1. Then we have another value on the y-axis where y is equal to 1, where it's defined. So we can basically see how we're going to be working this equation. We're going to be breaking it up into parts, specifically where y is equal to negative 2, the range of y between negative 1 and negative 2. We're going to be looking at y equals to 0, and we're going to be looking at y equals to 1. All right? And basically we're going to be putting our f of x, our little f of y terms, in terms of big F of x, which we'll get through in a minute. We'll talk about right now. So, if we break up our term, all right, we mentioned this right here. We're defined in this range. If we look first at y equals negative 2, we want the probability of y at negative 2, which we say here corresponds to the probability of x being greater than 2, which you can see right here. So the probability at y is negative 2. This line right here corresponds to all probabilities on the x-axis where x is greater than 2. All right? And the way we'd actually get that term is basically by taking 1 minus the big F of x at 2. Makes sense. For that range, which is defined by our negative linear term, we're going to have to use the fundamental theorem to actually calculate little f of y, which is basically little f of x divided by the absolute value of the derivative of our g function. Given that our g function is basically just a negative linear, the derivative is not surprising. It's just negative 1. Absolute value of that is 1. Now we see here by substituting in for x, we could easily see how we could switch the term x is equal to negative y, substitute in. So basically within this range, our little f of y is going to be equal to little f of x with the term negative y inside. All right? Now, the other two terms, y equals to 0 and y equals 1, is going to be figured out similar to how y is equal to negative 2. So y is equal to 0 is going to correspond on the x-axis to the probability between 0 and 1 on the x-axis, which makes sense. Here it is. 0 and 1 on the x-axis corresponds on the y-axis to y equals 1. All right? And that's just going to be a simple difference of the big F of x. So f of x at 1 minus f of x is 0. All right? Which makes sense. 1 minus 0, we're going to get that difference right there. And then for y equals 1 right there, it's going to correspond to probabilities less than 0. Makes sense. X is less than 0, where the y is defined at 1. All right, and that's just going to be defined as big F of x at 0. All right, so from that, we can actually get a final term for our little f at y. Basically, we define it by the individual functions, which you have up here. So 1 minus f of 2 right here. We actually define it at a delta function because it's a specific point. We throw that right in. Okay. But I also put it in like a semicolon and wrote it out that way. You can write it both ways, actually. This term right here corresponds to that. All right. We write it in unit function to actually show there's a range. The range is going to be specifically between right here, between negative 2 and negative 1, the way I wrote it out right here. But I could write it out like that. This corresponds to that right here. The delta function again corresponds to the y equals 0. And then finally we have big F of x at 0 defining where y is equal to 1. Okay? And everywhere else in the function is equal to 0. Now, if we actually draw this out, we can see the function right here. All right? So, here's our value right here. Delta function right here defined by an area of 1 by this function right here. All right? We have our curve right here corresponding to this function. All right? We can tell how that works out, like negative 1 right there. You can see how that works out. This is defined as that. All right, we have an empty term right here. Nothing's defined right here. Then we have two delta functions. One at 0, defined by that function for an area. And one at 1, defined by big F of x. There. And that's our formula for little f of y. Now, to proceed to big F of y, we're going to have to look at, we're going to be going through a similar function. I'm not going to get into it too much because I think it might get into a little bit too much detail. But again, we're defining our y between negative 2 and 1. We can see that in this case, because big F, cumulative function, for y's lower than negative 2, we're going to be equal to 0. And then for y's greater than 1, we're going to be equal to 1. All right? So we're going to be working in the same breakdown as our previous for little f of y to do big F of y. The first region we're going to be worried about is where we define that negative linear term between negative 2 and negative 1. All right? And the way we're going to actually derive our big F of y is by taking the integral of little f of y. And we define it by some random y, we just call it alpha in this case, between negative infinity and the value y, which we can break down even further because remember, we're only defined at right here, starting at negative 2. which we found the probability right here. So that's going to correspond to the integral from negative infinity all the way up to negative 2. All right? Then we can work the integral from negative 2 to y. So we break up the term like that. Then what we do here, we do a little bit of manipulation all around, okay? We make that negative, that's fine. So we can actually substitute a different variable term, dummy function, accordingly. We work it out into beta. What do we do? We actually flip the terms right here to get a negative. All right. I mean, like I said, I'm not going to get into much of the nitty-gritty. All right. We can actually break this down further. So basically, it's going to be equal to this. This term is going to be equal to this. And as we can see, this term basically is big F of x at 2. This term is going to be big F of x at negative y. So if we take the summation of these terms, it's going to be 1 minus big F of x at 2 plus big F of x at 2 minus big F of x at negative y. These two terms cancel. And our final equation for within this region, basically big F of y is equal to 1 minus big F of x at negative y. So that's going to be our term for this region right here. Now, between negative 1 and 0, given that within this range, the little f of y is equal to 0 in this range, basically remember how we have nothing in there. So right here, it's a jump term. All right, nothing actually happens, nothing's going to be gained, so nothing's going to really change in that range. It's going to stay exactly the same. All right, basically the value within our big f of y is going to stay how it was at y equals negative 1. Therefore, we can actually use this term, substitute in, and define this range by basically using this term and substituting for y equal to negative 1, which we do right here. So and get this function right here, which basically we're saying in this range right here, we define a constant 1 minus big F of x at 1. Here, from 0 to 1, the only value that we added was at y equals 0, which we said right here. Okay. We figured that out right over here, what that ended up being. Right there. So what we can end up doing for this portion of the equation, we just basically add this plus that term. All right, we add them together. Cancel out terms. It's going to be 1 minus big F of x at 0, and that's going to define the region from 0 of y equal between 0 and 1. And like I said, y greater than 1 is going to be equal to 1. So we've defined our big F of y as follows. For y is less than 2, it's equal to 0. For between that negative 1 and negative 2, we define it as that function. We also define the constant right here from negative 1 to 0. Another constant from 0 to 1. And for y is greater than equal to 1, we have it defined as 1. And we have the corresponding picture right here. As we can see, this is going to be the y-axis. This is the, sorry, I didn't label it, big F of y. As you can see, for less than negative 2y, it's 0. Then we have a jump. This term defined by this curve right here from negative 2 to negative 1. Then we have a constant corresponding to 1 minus big F of x at 1. We have a jump corresponding to, and this line corresponds to 1 minus big F of x at 0. And then we have a final jump to the value of 1, and then it's 1 furthermore. Hence our derivation of big F of y and little f of y.